All right, so we're going to try another example that involves a trig sub. I just tried shooting this video and made a mistake in my first step, so that's why this is all scribbled out. I figured I would rather just try it again, but sorry for the little scribble there. So if you notice what we have here, we have a definite integral this time. It's the first integral we've done in this section where we had limits of integration. And kind of like with U substitution, the limits of integration are going to change according to the substitution that we are making. So the integrand and the limits of integration have to change, and we have to think about both of those things. So how do we approach this one? Well, the integrand here looks kind of similar to the types of integrands that we've been considering so far in this section. In fact, referring to this table here that we did in the previous video, I have a square root, and within that square root there's an x squared showing up. But what's missing is this a squared that's showing up in all of these. Remember that a is a constant, and I don't have that in this example. I have an x instead. So how are we supposed to approach this? There's a handy trick that we can do to make a problem like this easier, and that's completing the square. So here's what I'm going to do. I'm going to take that definite integral, I'm going to rewrite it, and I'm going to leave myself a little bit of space right here. But taking a look here, for completing the square, the first thing you want to do is make sure that your x squared term is a positive 1. And right now it's not. It's a negative 1. So I'm going to start by factoring a negative out of all the terms here, which I can flip things around and write that as x squared minus x. So that's what I would have in parentheses here. This is actually the step that I forgot to do in my previous example. I started completing the square before pulling a negative out, which is why I abandoned that approach. Okay, now if you remember how completing the square works, what we do is we look at our linear term. That's the term that's just an x here. You take its coefficient, which is a 1, take half of that, which would be 1/2, and then square your result. 1/2 squared is 1/4. We add 1/4 to that. Okay, the purpose of that is that now the stuff in parentheses here is a perfect square trinomial. It'll factor down to a perfect square. The problem though is that I just added something new that wasn't there before. This 1/4 does not belong, right? In fact, it's not actually even a 1/4. Technically, it's a negative 1/4, because if I take this negative and distribute it back in here, I'd have a negative 1/4 right there. So I have to compensate by the negative 1/4 that I've just added into my radicand here by adding a positive 1/4 to compensate. And you should notice, like, if I were to distribute that negative in, I'd have a 1/4 and a negative 1/4. They would cancel out and take me back to what I had in the first place. So this is equivalent to this. Don't forget our dx. All right. The purpose of that is to allow me to factor that thing down. So now I have this. 1/4 minus, this would factor to x minus 1/2 quantity squared dx. Okay? Now this looks similar to the types of integrands that we have been considering so far. We have a constant minus, not an x squared, but an expression that's almost an x squared. So how do we approach this? Well, first of all, which of the expressions in our table is this most similar to? I have a constant squared minus an x squared here. That's the closest that I can get to this. So when we have this type of expression, we make the substitution a sine of theta, and we set that equal to x. What I'm going to do here is still use that a sine of theta, which in this case would be 1/2 sine of theta, but I'm going to set it equal to x minus 1/2. I'm going to set it equal to this, okay? So again, what I'm going to do is set x minus 1/2 equal to a sine of theta. Remember, a is coming from here, so that 1/4 is a squared, which means a would just be 1/2 sine of theta. Okay, now if I want dx, I can take derivatives of both sides. The constant just goes away, and I still get dx equals 1/2 cosine of theta d theta. Okay, now let's think about where these substitutions are going to come into play here. So looking at what I have, I'm going to make the substitution. I'm going to deal with the limits of integration in a second. Let's start with the radical here, my integrand. This is going to become the square root of 1/4. Now that x minus 1/2 in parentheses right there shows up here, and that I'm setting equal to 1/2 sine of theta. So this is equal to minus 1/2 sine of theta squared. When I square that, I get 1/4 sine squared of theta. I also have this dx here, which becomes 1/2 cosine of theta d theta. Okay, so I'm getting some useful stuff here, but I also need to worry about, or I need to consider what's going on with my limits of integration here. Now remember, these limits of integration are x values in this integral here, but I'm converting them to theta values here. And this is how I relate x to theta. It's my substitution. So let's see if we can do something here. Let me change the way that this looks. Actually, let's not even do that. Let's take the corresponding x values here and plug them into this x right here. So I'm going to take my 0, plug that in for this x right here, which would give me 0 minus 1/2 equals 1/2 sine of theta. And the goal here is to solve for that theta. Now, 0 minus 1/2 is just negative 1/2. And then I could eliminate this 1/2 by multiplying both sides by 2. This is going to give me negative 1 on that side equals sine of theta, which implies that theta is equal to negative pi over 2. Okay? So that's what the solution to this would be within the restriction that we've placed on our thetas. So this is negative pi over 2. All fine and good. So now, what about my upper limit of integration? This time I'm going to plug a 1 in. 1 minus 1/2 equals 1/2 sine of theta. In this case, 1 minus 1/2 is just positive 1/2. Multiplying both sides by 2 would give me positive 1 equals sine of theta, which implies that theta is equal to pi over 2. Again, remember, theta can only take on values between negative pi over 2 and positive pi over 2 inclusive when we make this type of substitution. And so that's the only possibility here. I get pi over 2 for my upper limit of integration. Now let's think through some of the other stuff that's going to happen here. So I have this 1/4 inside the square root here. That 1/4 I could factor out of both terms, take its square root to bring it outside of the radical. That would be 1/2. And then as a constant, I could bring it completely out of the integral, so I'd have a 1/2 out here. But you see, I also have another 1/2 right here that's multiplied to everything. That can also be brought out, multiplied to the 1/2 out there, and I'm going to get a 1/4 now. Okay, so I talked through kind of a lot of stuff, but basically what I'm doing is I'm managing all of these constants in here. Because that 1/4 was factored out, now I have 1 minus sine squared of theta under my radical times cosine of theta d theta. This I know. So write all this stuff in here. This is the square root of cosine squared of theta times cosine of theta d theta, because of my Pythagorean identity. Now, when I take a square root, as we've seen before, this just becomes cosine of theta, which, when multiplied to that cosine of theta, is going to become cosine squared. Okay? So I'm going to get cosine squared of theta d theta. How do we handle this? This is a trigonometric integral, and we have dealt with these types of trigonometric integrals before in the previous section. Here, the trick is to use a power reduction formula. So the power reduction formula is cosine squared of theta is equal to 1/2 times, in parentheses, 1 plus 2 cosine of theta. Cosine of 2 theta. The 1/2 that appears in that integral, or in that power reduction formula, I can bring that 1/2 out and multiply it to the 1/4 that's already out there. That's going to give me a 1/8. I have negative pi over 2 to pi over 2. And then since I've dealt with the 1/2, the only thing left from my power reduction formula is this. Okay? Now, as we have seen before, cosine and sine are periodic functions. And we talked about this in the previous section. If you integrate a sine or a cosine function over an interval that's equal to some multiple of the period of that function, it's always going to become 0. And that has to do with the fact that one full period of a sine or a cosine function will have the same amount of positive area as negative area under the curve, so that it's all going to 0 out. The cosine function here is cosine of 2 theta. This has a period of pi. Remember, the cosine function, just cosine of theta by itself, would have a period of 2 pi, but then we divide that by the coefficient here. 2 pi divided by 2 would be pi. Notice here that the interval I'm integrating over, negative pi over 2 to pi over 2, has a length of pi. The distance from negative pi over 2 to positive pi over 2 is exactly pi. So what that means is that I'm integrating this function over one of its periods, which means it's going to go to 0. That's a shortcut. Now, if you have a hard time remembering all of that, you can just integrate this directly if you want to. It's not hard to do. It just means it's going to take you more time. But really all this leaves me with now is that 1 right there. So I get 1/8. 1, when I integrate it, is just going to become theta. And that's going to go from negative pi over 2 to pi over 2. Now, in the previous trig subs that we've done, we've had to rewrite this theta back in terms of x again. But I don't have to do that this time because this is a definite integral, and we've accounted for this substitution with our limits of integration already. So there's no need to convert back to x's again because I've got the correct integral in terms of theta with corresponding theta values in my limits here. So this I just evaluate. 1/8 times pi over 2 minus 1/8 times negative pi over 2. I'll let you do the arithmetic on that. It's really straightforward. This comes out to just pi over 8. And that's our final answer for that one. Okay? Good stuff. So we've got 2 examples left. We should be able to do them both, I think, in this video. This next one here, hopefully you can see that. It's a little bit small, but we're going to evaluate this integral. It's dx over x squared minus 9 to the 3/2 power. So I'm not explicitly seeing a radical in there, but I do remember that rational powers involve radicals. So really this is the same thing as the square root of x squared minus 9 all cubed. That's how we interpret that. I'm not going to write that radical. I'm fine with the rational power being there, but I'm going to think of this as a trig substitution the way that I would if that radical was visible. So I have an x squared minus 9. If you refer to the table in the previous video, this is the type of trig substitution that would involve a secant function. So I am going to set x equal to, and remember it would be a secant of theta, where the a comes from this constant. So that's a 9, which represents a squared. That means my a would actually be a 3. 3 secant of theta, which means my dx equals 3 secant theta tangent theta, d theta, okay? Now I can go ahead and make all of my substitutions. So rewriting this integral using these substitutions, the dx is going to become this, 3 secant theta tangent theta. I'm going to put this d theta all the way out here. And then my denominator is going to become, so this x squared is going to become 3 secant theta all squared, which really is 9 secant squared of theta when I square everything, minus 9 to the 3/2 power. Okay? Now I can do a few things here to simplify. And you may notice by now, I tend to skip some of the smaller steps in these integrals because if I didn't do that, they would take much longer than they already do. So there's a certain amount of this that I'm doing mentally. which really you're going to want to be able to do as well. Here's the mental arithmetic I'm going to do. I have a 9 appearing in each term here. I'd like to factor that out, but it's stuck inside the parentheses where I'm raising everything to the 3/2 power. So if I factor a 9 out of both of these terms, I can't get it completely out of the parentheses until I take the 3/2 power of that 9. 3/2 power, that means I'm taking a square root and then cubing the result. So the square root of 9 is 3, and then if I cube 3, I get 27. That means a 27 is coming out of here. But then notice up here I have this 3. So now I have 3 over 27, which is 1/9. I can factor a 1/9 completely out of my integral, okay? At this level, at the Calculus 2 level, you actually should be able to do all of that mentally. If you can't, that's maybe something to work on, because there's a lot that still needs to be done here. Secant theta, tangent theta. Down here, I'm going to have secant squared of theta minus 1 now. I've dealt with the 9 that was there. That's to the 3/2 power. There's a d theta right there. So this guy right here, the whole point of this substitution was to get that secant squared minus 1, because that is the same thing as tangent squared. So I can write this as 1/9 times secant of theta, tangent of theta, all over tangent squared of theta to the 3/2 power, and there's my d theta right there. Now what I have is a power to a power, so I can multiply exponents together. 2 times 3/2 is 3, so I'm going to get this. Secant theta, tangent theta, over tangent cubed of theta, d theta. So I can already see some nice cancellation that's going to happen. This tangent is going to cancel with one of those tangents, leaving me with tangent squared down there. Okay? How do you take an integral of secant of theta over tangent squared? Well, I think what I would probably do is think of this as something you might see in a trigonometry class, where you want to prove a trig identity or simplify a trigonometric expression. I like to do that by converting things to sines and cosines. So for example, this secant of theta is the same thing as 1 over cosine of theta. That's the definition of the secant function. Tangent squared would be sine squared over cosine squared, but I'm actually dividing by that tangent squared, not multiplying by it. So I have to multiply by the reciprocal of that, which would be cosine squared over sine squared. Okay, now I see more cancellation happening. That cosine and that cosine squared. So now what I have is cosine of theta over sine squared. Okay? So cosine of theta over sine squared of theta. I can pull a cosine of theta and a sine of theta out as one of those factors, leaving me with a 1 over sine of theta here. Verify that this is the same thing as this. But we know that this is the same thing as cotangent of theta, whereas this is the same thing as cosecant of theta. And this I recognize as almost the derivative of the cosecant function. The only thing that's missing is a negative, but that's easy to compensate for. This would come out to negative 1/9 cosecant of theta plus c. Okay. Now, once again, we're not done yet because we don't want theta in our answer. We want x in our answer because that's what we started with. So back to the right triangle. Here's my right triangle. Let's identify that as my theta. And then how do I relate theta to x? I use my substitution, but I'm going to rewrite it as secant of theta equals x over 3. So solve for the secant of theta there. Okay, what is the secant function? It's the reciprocal of the cosine function, which is adjacent over hypotenuse. So we're actually looking at hypotenuse over adjacent now. X here, 3 here. Use the Pythagorean theorem. This would be the square root of my hypotenuse squared, x squared, minus that leg squared, which would be 9. Okay, and again, that x squared minus 9 is not a coincidence that we're seeing that here as well as here. That's, hopefully you're seeing that pattern, okay? All right, now what was the whole point of all this? I have cosecant of theta showing up here. Cosecant of theta is 1 over sine. Sine is opposite over hypotenuse, so this would be hypotenuse over opposite, which would look like x over that square root there, x squared minus 9. There was a negative 1/9 out there to begin with. The 9 from that can just get multiplied into the denominator, and I'll keep the negative on the outside. And then I have this plus c here. That would be my answer. Okay, pretty cool. One problem left to do. It's this guy down here. Now this integral of dx over x squared plus 1, this can be done with one of the trig substitutions that we've already talked about. You can do this one by substituting x equals tangent of theta, and it will work out just fine. But we want to see what an alternative approach could be. And that's going to be using a hyperbolic function. So if you remember your hyperbolic trigonometric functions, the sinh, cosh, tanh, those functions have their own sets of trig identities. And the relevant trig identity here, hyperbolic trigonometric identity, is this one. Cosh squared of theta is equal to sinh squared of theta plus 1. This is specific to hyperbolic functions, okay? So if you're looking at that and you're feeling like, that doesn't look right, shouldn't it be, cosh squared plus sinh squared equals 1? That's not correct, because that would be sine squared plus cosine squared. The hyperbolic functions have different identities. So this is valuable because I can make a substitution where x is equal to the sinh function here. So if I set x equal to sinh of x, I know from calculus 1 that dx would be cosh of x, theta. I need to make these thetas. I'm already using x, I can't reuse it there. Cosh of theta d theta, like that. Okay, so now going to my integral right here, this could be, I can make a substitution. I would get dx, which I said over here is cosh of theta, and then that d theta I'm going to put out here. Square root of x squared plus 1 becomes the square root of sinh squared of theta plus 1. And this is where that identity is going to get used. That radicand becomes cosh squared. So I get this, cosh of theta, over the square root of cosh squared of theta, d theta. The square root of cosh squared of theta is going to be just cosh. If you remember from your hyperbolic trig functions back in calculus 1, the cosh function is positive everywhere. So when I take a square root of cosh squared, the absolute value that would have appeared here is unnecessary because it's automatically going to be positive no matter what. So this is going to become cosh over cosh, which is just 1, times d theta, that's just d theta. That's about as easy of an integral as we could hope for. This becomes theta plus c after integrating. Now I can't leave it that way because the function that I'm ending up with is in terms of theta, not x. So we have to convert back to x's. Now these are hyperbolic trig functions. I can't use a right triangle for these. But if I look up here, x was defined to be sinh of theta, which would imply that theta is equal to the inverse sinh of x. So I could write that theta as the inverse sinh of x. And even though I could technically leave it that way, depending on your own preference, you may not want to leave things in terms of these hyperbolic trig functions. It's technically fine to do that. But if you recall from way back in chapter 3 that you covered in calculus 1, the inverse sinh function can be represented using a natural logarithm. It's actually the same thing as the natural log of x plus the square root of x squared plus 1. So either of these are technically correct, but depending on your preference, you may want to write it that way. All right, so that just about covers everything for section 7.3. And yep, that's it.